Hello, welcome back. We're in chapter 3. I guess I'm not going to make that go away, but that's alright. Here we are, dealing with uncertainty. Like when I'm doing these videos, you never know if I'm going to figure it out or not. Alright, so significant digits. Whew, I have a handout on this one too, and I'm going to include it both in the description of the video and on Canvas for my students. Which digits are significant? Now, all digits are significant to a mathematician, but we're talking about precision here. Like when you measure a door, right? Is it 7 feet or is it 6 feet 10 inches? How precise do you want to be? And so we have mathematical rules for how we deal with numbers. All non-zero digits, so 1 through 9, always significant. Zeros that follow a non-zero digit and lie to the right of the decimal point, always significant. If we put a 0 and it just doesn't make any sense why I would have to put a 0 there, it's because it's a significant digit. Or else I would write 4.2 or just 3. All right, if those were not significant, if they didn't matter. Zeros between non-zero digits, so those zeros are significant, they matter. And zeros to the left of the first non-zero digit are never significant. All right, so these are just placeholders just to get us there. All right, so they don't really matter. They're just to tell us a place value. Here, we have no idea if these zeros are significant or not because they don't tell us. This could be either 2 or 3 significant digits. This could be 1, 2, 3, 4, or all 5 as significant digits. It depends on the problem, and they have to tell you in order for you to know. Okay, so we're going to try to use this a little bit. Here we go. State the number of significant digits and the implied meaning of the following numbers. Now, we got time, length, weight, and a couple of populations. Let's take a look. A time of 11.90 seconds. Now, if I were to type this into Excel, it'd take that 0 off right away. A calculator, it wouldn't even count the 0. It'd be like, yeah, whatever. Right? But 11.90, since that 0 comes after the decimal and after a significant digit, right, any digit 1 through 9, we know that this 0 must be significant or we wouldn't have written it. And that tells us we have tenths, hundredths. We're accurate to the nearest 1/100th of a second. This is the type of thing they'll use for Olympic races, world track finals. Heck, even just a high school track meet, you'll get within a 100th of a second for accuracy. I need a length of 0.00067 of a meter. Well, there's only 2 significant digits. So we're accurate to tens, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths, right? A millionth of a meter. Note that we could write this number as 67 micrometers, showing clearly that it has 2 significant digits. We could also call this 6.7 times 10 to the negative 1, 2, 3, 4, 5. And in scientific notation, it's a lot easier to see that there are only 2 significant digits. A weight of 0.0030 grams, remember, placeholder, 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 significant. So there's 2 significant digits. The leading zeros are not significant. Wow, I was about to say something, I don't know what it was. We could rewrite it as 3.0 milligrams. The final zero is significant because there's no reason to include it unless we knew it, right? A population was reported as 240,000. The number has 2 significant digits, all right? We can only be sure of the 2 and the 4. Excuse me, the zeros that follow afterwards, we don't know if they're significant based on the information in the problem. And we're at thousands here, accurate to tens of thousands. But a population that's reported as 2.40 times 10 to the 5th, and keep in mind 2.40 times 10 to the 5th, I'm going to move my decimal 5 times. So there's 1, 2, 3, 4, 5. Oh, that's the same problem we had in part D. But now there's 3 significant digits. Although this is the same as 240,000, this 0 now shows a scientific, significant. Oh, too many S words. Scientific notation allows us to see significant digits so much easier. And this also tells us that we're now accurate to the nearest 1,000 people. Okay, so for each of the following operations, we're going to give our answer with the specified number of significant digits. Ooh, here we go. First, we'll take 7.7 millimeters and multiply by 9.92 millimeters and get 76.384 millimeters squared. Now, this is the answer that you get from the calculator. And because you know that. But look here, 7.7 has 2 significant digits. 9.92 has 3 significant digits. We're supposed to give our answer with 2. So we'll take these two, 76, and we'll just eliminate those 3. So we'll get 76 square millimeters. All right. 240,000 times 72,106. We're going to give our answer with 4 significant digits. This is a big number. What it looks like is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so if you were to do this on your calculator, you would come out with 17,305,044,440,000, whatever. All right, because we're asked to give with 4 significant digits, well, we already know those aren't there. So the first thing we did is we took this calculator number and we converted it to scientific notation. We want 4 significant digits. We have 1, 2, 3, 4. Because that 4th one is a 0 and next to it is a 5, we'll round it up to a 1. All right, 1.731 times 10 to the 10th. All right, so we round that 4th digit appropriately when we cut it off. Random errors occur because of random and inherently unpredictable events in the measurement process. All right, it happens. Systematic errors occur when there's a problem in the measurement system that affects all the measurements in the same way, such as making them all too high, too low, or too high. A systematic error might be a bad problem on a math exam that students cannot solve, right? So now all of the grades are off by they're all too low because I gave a bad problem, right? That's a systematic error. A random error, you forgot a negative sign, all right? Okay, sizes of errors. The absolute error describes how far from a measured value lies from the true value. Measured or claimed, whichever. Absolute error is measured value minus true value. Yeah, that should have came up separately. The relative error compares the size of the error to the true value. All right, so it compares the error to the true value, and we turn it into a percentage. All right, so let's find the absolute and relative error. Projected budget surplus of $17 billion turns out to be $25 billion at the end of the year. A budget surplus of $25 billion it's not actually good. They're not spending the money they need on their employees or what it happens to be. A budget surplus. That's crazy. Absolute error. 25 billion is what they had. They projected 17 billion, so they're over on their surplus of money by $8 billion. Whoop, whoop. The relative error is that 8 billion compared to the 17 billion that we projected. That's a 47.1% error. Somebody has some really bad projections. All right, really bad. Accuracy describes how closely a measurement approximates a true value. An accurate measurement has a small relative error. In my bathroom, I have a sliding glass door, and I need to measure this window. Now, accuracy is how well I find the distance here, right? How well do I find it? A precision, now that I have this measurement, and am I going to go in and tell somebody that it's 10 inches? It's so not 10 inches. It's like 27 inches. Or am I going to go in and tell them it's 26.75 inches, right? The precision is 2 significant figures or 4 significant figures. Did I get to the nearest quarter all right? Or was it just to the nearest whole inch? So rounding rule for addition and subtraction. When you are adding or subtracting amounts, use the same precision as the least precise number in the problem. If you're rounding for multiplication or division, round the answer to the same number of significant digits as the measurement with the fewest. Always, we go with the least precise measurements, the fewest significant digits. And also, this is major. This is like caution, downhill curves. Round only after completing all the operations. Leave all those numbers on your calculator. Leave them until the final answer, and then we round. Don't round in between. Intermediate rounding gets the best of us. So, a book written 30 years ago states that the oldest Mayan ruins are 2,000 years old. How old are they now? Well, because the book is 30 years old, we're tempted to add 30 years and say, well, the ruins are 2,030 years old. But 2,000 is the least precise of the two numbers. It's precise really only to the nearest 1,000, right? The 2 is significant and the zeros are not. Well, 30 years is precise to the nearest 10 years. Therefore, the answer should also be precise to the nearest 1,000. The least precise is 1,000 years. This is more precise, right? The 10 years. So what we'll do, a book written 30 years ago, the oldest Mayan ruins are, I went backwards? Nope, I went the right way. 2,000 years old plus 30 years old, precise to the nearest 1,000, precise to the nearest 10. Our answer is the year is 2,030 years, but we have to round to the nearest 1,000. When I round to the nearest 1,000, I'll look at the 0. The 0 tells me I leave that 2,000 alone, and the ruins are still just 2,000 years old. It doesn't matter. Unless the book was more than 50 years old, we would just call it 2,000. Given the precision of the age of the ruins, they're still about 2,000 years old, even though the book's written a while back. So the government in a town of 82,000 people plans to spend $41.5 million this year. Assuming all this money must come from taxes, what average amount must the city collect from each resident? We're going to find the average tax by dividing 41.5 million, which has 3 significant digits, and you'll find this a lot. This isn't straight up scientific notation, but the units of millions tells us that we only have 3 significant digits. The rest are just units. The 82,000, right? It's probably not exactly 82,000. It's probably 82,471. But they just said 82,000, which has 2 significant digits, just these 2. Population has only 2 significant digits. The money has 3, so we'll round our answer to match the 2 significant digits. $41,500,000 divided by 82,000 residents is $506.10. This is our calculator answer. Calculator is not wrong, but the calculator doesn't do significant digits. If I want 2 significant digits, I want my 2 significant digits here. Since 0 will be my second digit, I look at the 6. The 6 tells me to round up, and so that 50, or the significant part, becomes a 51. Zeros for the rest of it. It's about $510 per person in taxes. This is when we say about, right? Precisely, it's $506.10. But it's about $510. All right, that's it. Thank you once again for listening.